Hello, I am Professor S. Sankaran in the Department of Metallurgical and Materials Engineering. Hello, let us continue our discussion on state of stress in two dimensions. What we have just looked at so far is we try to kind of derive an expression for the for getting the principal stresses in plane stress condition or in two dimensions on an oblique plane. That means we are trying to find an equation which will help us to find the principal stresses as a function of any orientation. That's all we are trying to do. I'll just quickly review what we have seen yesterday, and then we would like to continue further. Okay. So if you look at what we have just seen yesterday is like quickly I will just go through. We have taken this kind of a geometry to describe this, and then we have taken a wedge out of this square member, and then we looked at the forces which is normal to this oblique plane. Then we try to do the force balancing, because we assume the strength of materials assumes that this is the member is in the equilibrium, and then we try to calculate the force equilibrium from each side, I mean for a normal stress as well as the shear stress, and then from there we calculated the expression for normal stress and shear stress in a general manner. So this is what we have just done yesterday. Okay. So these two equations, or I would say three equations, are very basic equations. Once we have this equation ready, then as you can see that we can do a lot of manipulation to get different quantities. For example, we are all interested, or especially in the theory of yielding and so on, or metal forming, the stress where it is maximum. For example, principal planes where the stress which is acting we are characterizing as principal stress, and the maximum shear stress, which plane we have to identify. So these are all some of the benefits of looking at all these equations in detail. So this we will see one by one. Then again we just discussed about these 4 points about the relation between the normal stress and shear stress, and the maximum and the minimum values of normal stress on an oblique plane through point O occur when the shear stress is 0. Just we looked at all these points, and the maximum and the minimum values of both normal stress and shear stress occur at an angle which are 90 degree apart. So this also we have just witnessed yesterday. The maximum shear stress occurs at an angle halfway between maximum and minimum normal stress. There was a typo error yesterday here. It was maximum and minimum normal stress. So that is what also showing in this image. And finally, the variation of normal stress and shear stress occurs in the form of a sine wave. So we are witnessing that as usual. So we discussed that, and we were trying to calculate the principal planes from these equations. No shear stress, that means the principal stress wherever the principal stress is acting on a principal plane, there is no shear stress, and its angular relationship with respect to xy coordinate axis can be found out from this shear stress equations. That means I'll just go back. So this equation we are talking about. So this, and then we have taken this relation, and then we are trying to manipulate that. And then if you rearrange these equations, then you get this tan 2 theta is equal to 2 tau xy by sigma x minus sigma y, which gives a idea of where the principal plane could be. And I just mentioned yesterday that you can use this on this right angle triangle like this. This is 2 theta. So then you can find out the hypotenuse values using this relation as per the Pythagoras theorem. Then you can see that sin 2 theta and cos theta value can be readily found out from this. It's a very simple step. And then what is the use of finding this? If you can find this sin 2 theta and cos 2 theta, then we can plug these values into the general expression which we have derived for sigma x prime and sigma y prime for finding out the principal stresses on an oblique plane. So that's what we have seen yesterday, and this is the final expression. Substituting this sin and cos values in equation 1 results in the expression for maximum and minimum principal stresses for a 2-dimensional state of stress. So this equation gives that. And also we stopped somewhere in this discussion. What we are interested is to find out the plane of normals, the orientation of a normal stress or a principal stress, okay, or a normal stress which contains both a shear and normal component. How to find the plane orientation, that is what we were discussing. So for that we take this diagram where it shows the biaxial stress sigma x and sigma y, and then this is a diagonal shear stress, and as per the convention, this sigma x is always greater than sigma y. That is, even if it is a 3 dimension, that sigma 2 will be greater than sigma 3. So that is a convention. So the figure shows a simple way to establish the direction of largest principal stress sigma 1. Sigma 1 will lie between the algebraically largest normal stress and the shear diagonal. To see this intuitively, consider that if there were no shear stress, then sigma x is equal to sigma 1. So if there is no shear stress, then we are talking about this direction, right? This direction. So, and if it is completely it's only shear stress, then it is this direction, right? Normal to the stress along the shear diagonal. If both normal and shear stress act on this element, then sigma 1 lies between the influences of these two, somewhere here. So this is a nice way of looking at where the sigma 1 will be, and we are interested in maximum shear stress, right? So especially in theory of fielding, sigma max is tau max, I would say, is very important parameter where the yielding takes place, and we will discuss that in detail in yielding theory and so on. To find out the maximum shear stress, we differentiate the expression of tau x prime y prime, what we have, the same equation what we have been using, and set this equal to 0. So this is what we get, and this you can just rewrite in this form: tan 2 theta s is equal to sigma y minus sigma x by 2 tau xy, and this can be rewritten like this for our convenience, because we have another expression for tan 2 theta, right? Just before we have just seen where it was giving some angular relationship for the principal planes, right? So that tan 2 theta was describing the angular relationship for the normal stress, and this is for a shear stress. Okay, so we can now compare these two. Comparing this with the angle at which the principal planes occur, that is equation 4, we see that tan 2 theta s, that is tan 2 theta representing the maximum shear, is negative reciprocal of tan 2 normal. Okay, so this is a negative reciprocal of this means that 2 theta s and 2 theta n, it should be supposed to be n. 2 theta s and 2 theta n are separated in space by 45 degree. So, you see that by looking at these expressions, which is also gives a very nice idea about the orientation between these two planes. We have also physically seen that how these two are separated, but these equations also prove that the orientation between these two stresses. Okay, so that's anyway. This is a permanent correction I will make, so it will be n. It's supposed to be, it should be read as an n. So, what is the maximum shear stress? The magnitude is given by tau max is equal to plus or minus sigma x minus sigma y by 2 whole square plus tau x y whole square to the power half. So, this expression is important, and we will now move on to something a new way of representing the stress versus strain. So, very useful graphical method for representing a state of stress at a point on an oblique plane through a point suggested by Mohr. Okay, there is a scientist suggested this methodology. So, it is called Mohr circle. So, what does it convey? But before we go into the details of what this Mohr circle means, what we will do is we will take I have just written an expression here. How do we got this expression? I hope you all will have the familiarity with these terms. What I have done is, you have the two-dimensional principal stress expressions and the shear stress expressions, right, for an arbitrary orientation. So, what we have done is, we have taken the 2 theta terms one side and the non-2 theta terms other side, added up, squared and added up. So, that is what it is. So, if you look at that, two equations, the shear stress expression as well as the normal stress expression, I have combined and separated the 2 theta terms right hand side and the non-2 theta side. To eliminate the 2 theta, we are doing this manipulation, and to get some expression what we get. So, that you can readily do. We have not changed anything, we have just rearranged those two equations and squared them and added up. So, you can just verify that. So, this can be written like this, rewritten like this, a simple rearrangement, and finally you get this sigma minus sigma x plus sigma y by 2 whole square plus tau xy square, which is equal to sigma x minus sigma y by 2 whole square plus tau xy square. Okay. So, this equation is in the form of sigma minus a to the power 2 plus tau minus b square is equal to r square. So, this equation is very familiar equation of circle. Okay. So, where a is sigma x plus sigma y by 2, b is equal to 0 and r is square root of sigma x minus sigma y by 2 whole square plus tau xy square. So, this is exactly the equation of the Mohr circle, the circle. So, this is representation, this way of representing this state of stress, okay, in 2 dimension is called Mohr circle. So, we will see what is this Mohr circle looks like. So, you can look at the member which is subjected to biaxial tension sigma x and sigma y, and then this is the shear stress acting. For this situation, and if it can be of arbitrary orientation, it will be rotated with respect to theta like this. So, for this situation, the Mohr circle is drawn here. So, what is involved in this Mohr circle drawing? So, the x-axis is principal normal stress, and y-axis is shear stress. Okay. So, that is the axis labeling. This is positive and this is negative, and this is positive and this is negative. And suppose if you take the any sigma x, which is normal to this any plane, if you can just mark it like this, positive and negative, AB, if you mark it like this, the intersection is considered as a center. Okay, intersection is the center of the circle, and then what you see here is D and E, where the shear stress is 0. That means at these 2 points it is pure principal stress, right? There is no shear stress, and the sigma x, that is where we are interested. So, you can see that this is this point sigma x, and the corresponding value here is, this is tau. So, what you are seeing here is plus tau xy, and this is minus tau xy. So, for example, if you like I just mentioned yesterday, so this shear stress will drive this direction, and this shear stress will drive this direction. So, this is a positive direction. So, the positive shear is here, put here, and then the negative is here, and the maximum the sigma 1, which is algebraically largest normal stress, is sigma 1, and what we are interested in plotting this is sigma x. So, the angle between this sigma 1 and sigma x is 2 theta. In Mohr circle, it is always the theta is plotted as a 2 theta, not just theta. So, it is always 2 theta, and then you can see that the angle between this sigma 1 and sigma x is 2 theta, and this is a sigma 2, right, sigma x, and this one is sigma x, and this one is sigma y, and this one is sigma 2, right, and this is sigma 1. And what is the maximum? Maximum is here, that is tau max, right. But we are interested in looking at this particular sigma normal stress, which is on an arbitrary theta. Then this diagram is useful because it can take any angle, right. So, any angle it will plot here, then you will see the corresponding normal stress and the shear stress here. So, here it is negative shear stress, it is positive shear stress. So, depending upon the rotation, which sign we are looking at, so we can easily relate this very nicely. You can represent the normal and shear stress for a given orientation. So, that is the usefulness of this state of stress. So, we can also look at the equations which we have derived, but this will give much more a visual benefit, right. So, grasping the idea of how to see this shear stress and normal stress as a function of orientation for all the orientation, you can see. So, this is for 2 dimension, and we now will slowly move to the state of stress in the 3 dimension. Okay. So far we just looked at biaxial. So, biaxial, when we say biaxial, sigma 1 and sigma 2 are supposed to be equal in magnitude, right, biaxial. And in general, the 3-dimensional state of stress consists of 3 unequal principal stresses, right, acting at a point. This is called a triaxial state of stress. So, you can have unequal principal stresses. Even in biaxial, you can just check whether it is equal in magnitude or unequal in magnitude state of stress. But in general, this is a three-dimensional state of stress can be an unequal principal stresses. And if the two of the three principal stresses are equal, then the state of stress is known as cylindrical. So, even in a triaxial state of stress, if out of three, if the two are equal in magnitude, the third is smaller than the other two, then it is called cylindrical. And if all the three principal stresses are equal, then the state of stress is said to be hydrostatic or spherical. So, these are the terms which is very important and very basic, and you have to keep in mind while describing the state of stress, especially in 3 dimension. Okay. So, we know now triaxial state of stress, cylindrical state of stress, and hydrostatic state of stress or spherical state of stress, how it will be, right. So, now we are just going to describe how to get this equations for the state of stress in 3 dimension. It is simply an extension of what we have just looked at for a 2 dimension. So, I am not going to just spend more time on this, but just for a completion, I wanted you to look at it, because you should not ignore this. And we are going to take up this same kind of Cartesian coordinate what we have done in 2 dimension. So, you just take this JKL plane, which is a plane which is just cut from in the cube, perfect cube, okay, kind of 1 1 1 plane, okay, and then all the and then here is the sigma, a normal stress which is coming out of this plane, and then we can just look at all these, these normal stresses are marked sigma x and sigma y with the 2 shear stress. So, this is what we have just seen yesterday. We need to resolve this total stress into normal stress and shear stress while we describing the state of stress in a 3 dimension. This is what we just looked at yesterday. So, like that we have just marked all this shear stress components as well as the normal stress components, and yeah. So, what we are now going to do is just I will very briefly describe this, the components of sigma. So, the component of sigma along each of the axis are capital Sx, Sy and Sz. So, in a 2-dimensional, if you go back and look at this geometry what we looked at it, we took a component, normal stress component, shear stress component on each direction. There it was just a line, right. We assumed that is a line because we just took a projection of an oblique plane. Here it will be, since it is a 3-dimensional, it will be a plane. So, we will consider the plane, okay. So, these are the components. So, the Sx is sigma L, Sy is equal to sigma m, and Sz is equal to sigma n. So, L, m, n are the direction cosines of sigma, which it makes with the x, y, z coordinates, okay. That is one thing you have to remember. So, the components of the stress, normal stress is you have to multiply with the direction cosine. And as I just said, the 2D plane, what are the 2D planes here we have to think of? KOL, KOL is this KOL, and that is the area of the triangle is A, and this is belong to x direction. So, it is multiplied by L. So, area JOK, this plane, that is associated with the y, so AM, okay, and then area JOL AN. So, this is a similar way what we have taken. So, now we will take the summation of the forces. Again, the assumption is same, this body is assumed to be in equilibrium. So, we take the summation of forces on a particular direction and we equate it to 0, then we are interested in the sigma normal stress to this plane KJL, and that area is A, and we are interested in L. So, sorry, that is x direction. So, we are interested in x direction. So, that is why it is sigma AL. That means a stress into area. So, it gives a force, right. So, exactly similar to what we have done in the 2 dimension. So, here also you just look at it without any problem. So, if you sum it in this direction, then sigma AL minus sigma XAL minus, this is x component here, and minus tau Yx AM minus tau Zx AN. So, you look at this x component here. So, they are all summed up here and then equated to 0. Then it is next is very simple step, rearrange them and then you get the expression like this. And similarly, you can do it for y direction and z direction. So, these are 3 homogeneous linear equation, and the non-trivial solution is only can be found out from the finding the determinant value. So, you can just put them into this determinant, and what you can see is the solution of the determinant results in a cubic equation in sigma. So, this is how the if you expand this determinant, you will get this expression. So, this all very simple operation, but what you can now observe is there is a combination of stress associated with each of these sigma. So, what it is, that means the 3 roots of the above equation are 3 principal stresses, sigma 1, sigma 2 and sigma 3. Okay. So, this combination of stresses associated with this coefficient of sigma, they are not going to change even if you change the coordinate system, any different coordinate system, and that is why they are called invariants, stress invariants. So, you should know what is stress invariant. So, these are the combination of stress coefficients of sigma. The first one invariant is sigma x plus sigma y and sigma z, that is I1, and then I2 is written like this, and then this is an I3. Okay. So, these are the 3 invariants of this cubic equation. Okay. This is the solution of this cubic equation. So, we will just refer this invariants when we look at the when we apply this concept into deformation much more, then you will get the grip of what are we talking about. Okay. So, let me number these, and what we have now seen here so far is a normal stress, principal stresses in 3 dimensions. Similarly, we can also look at the normal and shear stress on any oblique plane whose normal has a direction cosines L, M, N in with respect to x, y, z axis. So, the one thing we have to remember here is the total stress on the plane will not be coaxial with the normal stress, and so this condition exists there. So, once again we try to resolve these components in order to find this normal and shear stress. This exercise we have done already. So, it is in 3 dimension, you have one more extra term here. So, the resolved component is s squared is equal to sx square and sy square plus z square, and taking summation of forces in all these 3 directions, we arrive at the expression for orthogonal components of the total stress. So, this can be expanded it like this. So, we are trying to resolve this. Yeah. To find the normal stress sigma on oblique plane, it is necessary to determine the components of sx, sy, z in the direction of normal to the oblique plane. Thus, we write sigma is equal to sxl plus sym plus sszn. So, you plug in all these values here and then you get this expression. Okay. So, again the magnitude of the shear stress on the oblique plane can be found from tau square is equal to S square minus sigma square, which comes from this, right. So, these are all simple ways of looking at how we can visualize this normal and shear stress, and then we can also work out little more detail to get this expression. Let me finish that. And why are we looking at it? Because in a plasticity we will be using the shear stresses quite often, and it is also important to identify the planes on which the maximum and principal shear stress occurs. So that's another idea. So we know that already. This aspect we know this, that is tau max occurred on a plane halfway between the two principal planes. Therefore, it is easiest to define a principal shear stress in terms of three principal axes 1, 2, 3. Okay, and we can show that this the previous equations from there we can just we can also show that the tau square is equal to in the form of LMN, the direction coefficients, right. For to look at the principal planes we can use these terms. And there is another way, since they are all direction coefficients between normal to the oblique plane and the principal axis, the principal shear stresses occur for the following combinations of direction cosines that bisect the angle between the two of the three principal axes. So this is very interesting. So you can just specifically find out what combination of this direction cosines will give what type of shear stress combinations, right. So this is what it is. So if you can plug in this values of LMN, then you get this kind of a 3 by 3 matrix where you can see what type of shear stress or what type of shear plane will be operating in if this is or the direction cosines. Okay, so you will get tau 1, tau 2 and tau 3. Okay, so this you can just put it as in the form of graphs we can put, and I will just first show this and then we will talk. So this is the a pictorial representation of this two planes, right. So according to the convention, this we have already discussed, sigma 1 is the algebraically greatest principal stress and sigma 3 is the algebraically smallest. So tau 2 has the largest value of shear stress and this is called maximum shear stress tau max. So this we know, this is very important, and we know this is a maximum. Tau max is equal to sigma 1 minus sigma 3. So if you look at the table also before, tau 2 is the maximum. So these are the three set of principal planes, right. Actually you can see that if you look at this diagram, one thing is very clear. For a given pair of normal stresses, there are a pair of principal shear planes which bisects the normal stress, right. Here also it bisects and here also it bisects. So so you can also see that similar things are happening here for the tau max, and then this is a tau 2. So what we are now trying to convey through all this derivation, we are not only physically able to see how it is the principal plane or principal plane where the principal stress acts, the principal plane where the principal shear stress acts, and how they are connected angularly. These are all the things we have witnessed with this kind of exercise. Okay, it may look little boring or tiresome, but if you look at the end of what you can just grasp out of all this derivation, then it's not a bad idea to go through this, right? Okay, so this is about the state of stress in 3 dimension.